Yeah.
Okay. Welcome back to this very nice symposium commemorating Konrad. And the next speaker is Tomasz Lipniacki from the Institute of Fundamental Technological Research of the Polish Academy of Science. By the way, institute known to me from very early childhood because my father worked there. And now Tomek is there, and Marysia, who is, where is she, Marysia? Somewhere sitting, somewhere over there, is also working there. And he has collaborated with Konrad on different kinds of problems, and I think he'd tell us something about it, maybe. Go ahead.
Yeah, first I really would like to thank the organizer for having me here and for allowing me to present something about our joint work and about next works that follow, in a sense, from what I have been doing with Konrad. I quit being working in fluid mechanics. I found that it was by far too difficult for me and switched to biology. And now I am running the biology lab, and I would like to, at the end of my talk, I would like to tell you about some issues connected with biology in the area of partial differential equations that were motivated by our joint research in the area of superfluid vortices. So, when listening to the previous talk, I realized that my talk can be a little bit more technical. So I will be showing some equations, but I will not talk about these equations. So for people who are familiar, okay, please read the equations. For people who are not familiar, just try to follow me, and I will try to explain this concept in really simple terms. So what interested me for a very long time, and Konrad also from a different perspective, I came from the superfluid society, and Konrad came from magnetohydrodynamics and hydrodynamics. So in the context of superfluid, what is very important are the superfluid vortices, and what is characteristic for these vortices is that they are very thin. I mean, the thickness is the order of the helium atom, so it is of order of 1 angstrom. Okay, and their motion can be described by the so-called local induction approximation. This is, of course, approximation. And what is important is that the motion basically has two components. One is along the binormal, and it is proportional to the curvature. So the vortex ring tries to propagate along its axis. And the other term comes from the interaction with normal fluid, which is non-zero in the non-zero temperature, and it makes that the vortex ring shrinks. So this is component along normal, and it's also proportional to the curvature. Okay? So the more accurate description is by Biot-Savart law, when the motion of a given point of a vortex depends on this integral along the vortex and the other vortices. What people thought about the motion of these vortices was motivated to the large extent by the work of Schwarz, who analyzed the reconnections of quantum vortices. And when these two vortices reconnect, then the cusp is formed, and there is a very characteristic part of the motion, at least local. So you can learn quite a lot by simply observing this equation. You can see that this equation is invariant to the transformation in which we increase the spatial scale. This is the arc length of the vortex. So this is velocity. This is this term proportional to the binormal and normal. So when we do such transformation that we increase the scale, we make this vortex larger, and then we change the time, we multiply time by lambda squared, then we can find that this motion is identical. simply the vortex will move because all these two terms will be lambda times smaller, the vortex move lambda times slower, and because the distances are lambda times larger, then we have to rescale time. Okay? And it suggests that the vortex motion have self-similar solutions. So we may have solutions in this form, and typically, in many cases, instead of that equation, you can write equation for curvature and torsion. So when you there's also class of solutions. I can call them quasi-static. So there are solutions when basically the quantum vortex shrinks when alpha is non-zero. When the quantum vortex shrinks, when alpha is 0, when the vortex does not shrink, and there is infinite family of invariants. Renzo, present here, was working on this, and the motion is fully integrable. But when alpha is non-zero, then the vortex shrinks. So despite it shrinks, it may become identical when you reparameterize it all the time, instantaneously. Okay, so, but I will focus on self-similar solutions. So when you rewrite this equation in terms of curvature and torsion, you are getting to that nasty equations. And I was working on these equations when being with Konrad in Exeter, visiting Andrew Gilbert. I remember the very clever advice of Konrad. This calculation was really tedious, and I made plenty of mistakes. And Konrad told me, do it in small print. Smaller print, less mistakes. And it really works, because if you are doing it in a small print, you have to concentrate. Yeah? But anyway, I was close to abandoning. But finally, I realized what should be, if we are interested in the self-similar solution, what should be the initial configuration when we go with time to 0? What should be the initial configuration? Okay, and if the solution is to be self-similar, then the initial configuration must be the curve which has no scale. So what is the curve without scale? Straight line is the curve without scale. If you increase it or if you shrink it, it is identical to the initial curve. Okay. The two half lines with the common origin is the curve without scale again. Okay. And what is the most general curve without scale? So the most general curve without scale is combination of two logarithmic spirals with common origin and common axis. So there is a 4 parameter class of such curves. So basically, when you shrink this curve, it corresponds to rotation. When you shrink the logarithmic spiral on the cone, then it corresponds to rotation. Okay, so all these solutions, it can be demonstrated that all these similar solutions in the infinity became logarithmic spirals on the cone. So instead of really solving this equation, I found the solutions in the infinity. I found the convergence and found the solution in the simplest case when the initial configuration is composed of two half lines. And these solutions are important because they arise in reconnections of quantum vortices at a given angle. This is the original picture from Schwarz, and in this case you can explicitly or implicitly, in a sense, derive this solution. Okay, and these solutions were numerically observed by Schwarz many years ago. Okay, So this is the original first slide from our joint publication here in the Newton Institute. So when I was referring this to Konrad, I told him that these solutions exist until the angle between these two reconnecting lines is not too small. If the angle is below 8 degrees, then this solution does not exist because this line would have self-crossing. And I remember Konrad told me, okay, your solutions are interesting, but the most interesting is the situation where they do not exist. Okay, and we really start working on this, and the first question was whether also we obtain self-crossing when we do, instead of localized induction approximation, when we do the full Biot-Savart law calculations. And we asked Miron Kurza, it was our joint master degree student, and he checked that if we do it Biot-Savart, then even the angle can be a little bit larger and we obtain self-crossings. Okay. So then in fact Miron, I mean, he was extremely skillful person merging physics and informatics, did the check for Gross-Pitajewski equation, which described the let me, I hope I can run this. Okay, so what you can observe, this is the simulation. So it shows that really this self-crossing show up, and it implies that when we reconnect two lines at the tiny angle below 10 degrees, then we will obtain cascade of vortex rings, very tiny vortex rings. So this is the picture from our joint publication, and this shows the simulation in Biot-Savart law, and then in more detail at Gross-Pitajewski equation. So we propose that this mechanism can be important in the limit of zero temperature for dissipating the line length of vortex tangle, and that way dissipating the energy. That there are some reconnections at the tiny angle. It is known that vortices before reconnection, they like to become almost antiparallel, and they reconnect, and it leads to cascade of vortex rings which are so tiny that they propagate away of the tangle. I know Renzo made and Berengi also made a number of simulations showing how this tangle can evaporate. Okay, and now I think that it is nice if the science, in a sense, continue even if we are changing the subject. So I want to tell you what we learned from studying superfluid and some and the concept we learned, and it motivates my further work in the, say, biology. I mean, for biologists, these are rather PDEs than biologists, but okay. So there are two important concepts which arise for superfluids. One is reconnections, and the other is spinning. And in my understanding, these two phenomena comes from the fact that the vortex line likes to minimize its length because the energy is proportional to the length. So when we have the situation that there is no external flow, then this vortex will assume such position. if there is some external flow, normally it will move like this, but when it finds these two small hops, it can be pinned here, okay? So, and also reconnection is associated with minimizing the energy, because after the reconnection, there is a plenty of room for vortex shrinkage. So after these two lines reconnect, these vortices can shrink, okay? So, this work is in revision now. I hope it will be soon published. So it is about the pinning of traveling waves. So let's take the, say, canonical reaction diffusion equation. So this is the diffusion term. This is some source term. And you can easily realize that this equation is a stationary counterpart of Euler-Lagrange equation for such energy functional. Yeah? When V is the integral of the source function, so this is potential, and this is term associated with the first derivative of U. Yeah? So the energy is a combination of potential and of term proportional to the square of second derivative of U. Okay, and now if F is bistable and then U is the potential with two minima, you may have traveling wave solutions in which in one infinity the solution is equal to -1 when the potential has one minima, and in the other infinity the solution is equal to 1 when the potential has the other minima. And of course the traveling wave will propagate that way that the area occupied by the lower energy minima will increase. Okay? So this is very basic. What is interesting is that say that this is the domain, and this traveling front, this is a line around this domain. So this is three-dimensional domain, and we are considering traveling front on this domain. Okay? So this line will propagate, but at that point, in order to further propagate, the front line has to expand. And because there is some energy associated with the front line. Why there is energy associated with the front line? Because on the front we have to pass through the energy maxima. So we are connecting two energy minima in one infinity, in the other infinity, but on the front we have to pass through energy maxima. So the front, so here the front propagates because the energy of the red solution is lower than the energy of blue solution. But here it stops because the front elongates and it needs energy. Okay? And so here are some numerical verification that we can really predict when this front will stop. Very similar. No, I need it. The very similar solutions you may obtain for two-dimensional fronts, which are part of the sphere. I mean, when these solutions are considered not on the volume surface but inside the volume, equations are very similar, and also there is a front state front within the volume. This is important because it was shown that for that type of equation, there are no non-uniform solutions when the domain is convex. So you need concave domain and the place when it expands to obtain these solutions. And we propose that these solutions can be responsible, this is why this is biology, that these solutions can be responsible for polarization of such objects that can resemble biological objects like bone or budding yeast or adherent cells with four protrusions. So this can exist on the surfaces, and it can also exist within these domains. Okay, and as I said, the second property of quantum vortices are reconnections. So the fronts can also reconnect, and these reconnections in a special geometries. We are considering here geometries that resemble the dendritic tree. So when we have neuron collect information by its dendrites, and then it sends this information by axon. So there is a tree of dendrites. So you can imagine that there are two dendrites. So this is connected to axon of a given neuron, of some neuron. This is connected to the axon of the other neuron. And these two dendrites connect here, and then these two dendrites, so it makes the tree, it connects here. So as I said, because there is opening here, the front to propagate further, it has to increase its length. Then there is a stationary solution when this front gets stuck here, and this front gets stuck here. Okay, but this front is free to propagate. Okay, so finally these two fronts merge, they reconnect, and now this front can propagate and shrink, so it is very eager to propagate. So it will propagate up to merging with, up to reconnecting with that front, and finally it propagates. And this front reconnection is really connected with the details of geometry. So what we are proposing is that the phenomena of reconnecting traveling fronts, which like to reconnect because it allows them to minimize energy, can be responsible for logic gates in the dendrites trees. And because it depends on the details of geometry, it can guide some learning that when one dendrite becomes thicker, then this logic gate N can be replaced by no gate, that it will be sufficient to carry out the signal through the thicker dendrite, and this thinner dendrite will be only small obstacle that can be common. Okay, so I would like to finish with this. Maybe I spent a minute. Okay, so what I wanted to show is that it is not surprising. I mean, people know that the equations from the one discipline can bust the other discipline. Here it is not in fact equation, but the concept that we have, like in the case of quantum turbulence, we have one-dimensional singularities, which have a specific behavior because the energy is associated with the length of that singularity. So for example, these quantum vortices have to be perpendicular to the boundaries. Yeah? And also the front lines are perpendicular, I mean the front surfaces is perpendicular to the boundary, also by the energy minimization. And this leads to phenomena like pinning, which is observed for traveling fronts in the very classical PDE equation, and to reconnection of traveling fronts, either lines or surfaces, because it leads to minimization of front surface or front length. So I am really, in a sense, thankful to Konrad that he was working with me on the quantum vortices. He was not, I mean, I bring the quantum vortices to our table, but he was asking the question to allow us to do this research in the quantum vortex cascade and allow me to think about this dynamic in a broader sense. We have seen the genealogy or school genealogy of Konrad, and what is in a sense amazing is that that there's a number of people who graduate the same school. I graduated the same high school as Konrad 9 years after the school. Andrzej and Marysia are his classmates. My daughter, who is present now here, is hopefully graduating from that school in a year. So it is like a little bit surprising that it can be a school that students from that school, like in a sense, keep together and keep in science.
These are the links.
Yeah.
Any penetrating questions regarding some of the formulae that we've seen here?
You
Patrick.
reported Schwartz. Was that Bill Schwartz?
No, it was. What was his first name? It was Keith.
All right. I just wanted to.
Too difficult question.
A simpler question.
I'm sorry, but I'm pretty sure that never. I started working on that subject because of his works. It was at the time when there is internet was not existing in Poland, and we had access to Physical Review B, and it was the first papers I read on superfluid turbulence. So I have photocopies of his papers. So in fact, I should remember perfectly his name, but I'm pretty sure that it was never given on the paper, that there was only initial, and the initial was
His
K.
initials are KW.
Yeah, KW. This is what
W could be Bill.
Yeah. So I remember perfectly his initials, but I never was enough eager to check his name. Sorry.
Renzo?
I don't know. These fronts you mentioned are themselves locus of minimum energy.
No,
No.
these fronts are a locus of the maximum energy.
Of maximum.
Okay. So the one minimum is here. This is the lower minimum.
Right. Ah,
So
okay.
this area,
yeah.
so this area is expanding normally.
Is the maximum
This is
usually
the-
between minima.
Yeah, this is the minima of energy, but this is the higher minima, and this is when we have to pass through maximum. So normally, in the front, my time its length or its cross section, it propagates because this energy is lower than this energy. But here, it has to expand, and it connects a lot of energy because it is when the solution passes through the highest energy.
Thank you.
I have just a short remark that I recall Konrad on many occasions saying that the most important and often the hardest bit is to ask the right questions. So, yeah, that was very
This
good.
is an example, yeah.
Yeah.
Other comments or questions? Okay, then let's thank Tom one more time.